In this episode, we're going to look at the teach interface in Robot Programmer, and we're going to learn how to teach robot arc welding paths using the geometry that comes out of SolidWorks. So let's get started. Okay, so now that we have our simulation states all set up, let's discover how to teach the robot and program it. So programming for arc welding, there's a couple of different tabs we're going to work with. One's programming and one is arc. So what we'll do first is introduce the teach interface. So when we click on teach, it wants to know what we're teaching. And one of the things that you need to do before you start teaching is set the robot as the ASO, or the active simulation object. And what this does is this ensures that when you are programming, the interactive browser is going to give you information about that robot. So if I have multiple robots, for example, what is in this behavior tab will be based on which robot I set as the ASO, or active simulation object. And to set the active simulation object, you click on it, and there's a little icon right here, which is actually a button. And when you click that, you'll see a little swirl for a second. It'll think about it, and then it will make that the active simulation object. That way, you know you're looking at the information that you're dealing with. You'll also notice that there will be a Profiles tab when the robot is active. And the Profiles tab that you're looking at right now is the default. So in looking at the profiles, you'll notice that all of these profiles are from the Delmia robot library. These are just default values that come with the robot, and they're all different depending upon which robot you choose. The only thing that does not come out of the robot library is the tool profile. This tool profile is a result of us mounting this torch on the end of the robot. And what it did was it just took the value of this location on the torch and put it into the profile of the robot. All of these different profile values can be created by the user, or they can be uploaded from the robot. Specifically, when you're doing a simulation with the robot and you're planning to do offline programming, in other words, let's suppose that I have a robot and it's already manufacturing something on the floor. Let's say that I have a real robot and it's doing some arc welding on this control arm, but I want to change the program or put a new program in it. It's ideal if I can use the same motion profiles that I use on the real robot in the simulation, as well as the accuracy profiles as well. Many times on the manufacturing floor, they will take the values that they don't want to use and they'll delete them, or they'll change the values based on what the people on the manufacturing floor are used to seeing. They'll have programming protocols that they use so that they can narrow down the amount of data that the programmer on the manufacturing floor needs to know about. So they can create their own set of profiles on the production robot. And so if you're doing a simulation, you want these values to be the same as what is on the manufacturing robot on the floor. And the way to do that would be to upload the program from the manufacturing robot before you start programming it. Now you can upload the program and it only has to be one location from the robot on the manufacturing floor. But what you would do is you would take a robot controller dump and you would bring that into the simulation environment. So when you upload the robot program, you have all of the attribute files next to that program. And when you upload that program, it would suck in all of these parameters and all the values. And that way you have a one-to-one match on parameters from the simulation to the manufacturing floor. So let's talk about teaching the robot. Right now, we're going to talk about creating a robot task, okay? And I already have one in this robot, which I can delete. So I'll right click on this and say delete. Whenever I click on teach, it wants to know which robot are you talking about, and I pick my ASO, my active simulation object. Once that happens, you'll see I'll have a teach parameter box. I have my teach panel, and this is where when I record all of the points, they'll all be listed here. I'll have a place to hit record, so I could record Cartesian target, I could record a joint target, I could record a tag location, a home target. And so these are the different types of points I can record. Here's my modify current tag. Here's my delete. And so what I'll do is I'll go through and I will show you the individual functions and how they work. So what I would like to do is move the robot somewhere and hit record. So let's suppose that I just move it and I'm going to record a tag target. Tag targets are nice because you can visualize them. Then the tag is motion 1, robot motion 1. Here is the name of the tag right there. So when I recorded that, it's a joint move. And the reason it's a joint move is because of the settings that I have laid out in the teach parameter box. You'll also notice that the motion profile has a speed of 50%. Again, that comes from the teach parameter box. It's a fine move. Okay, and so this teach parameter box needs to be defined before you start recording your robot path. You'll also see that I have joint moves set up. So anytime I click on one of the record buttons, this is the information I'm going to see, and that is all of the parameters that will be set according to when I hit record. So you would want to make sure that these parameters are set according to the type of work you're trying to do. And make sure that you have the appropriate U-frame and U-tools that are being used for each operation. Okay, so now that we've covered the teach parameters, now let's take a look at the teach box. So as you hit record, each individual point will be listed inside of the teach interface. The teach interface will show point by point by point each individual location in the robot program and will also show all of the information that's associated to it. Which U-tool you're using, what speed you're associating with your motion and your motion type, and the name of the task and the name of the individual point. And as you click on them, the robot will move to them. Okay, so think of robot task as the name of the program, because when you download it, this is the name that it will be under. This is the name of the individual points. This interface is also modifiable. You can right click and then you can tell it that if you want to hide a column, and if you have a column that isn't being shown, you can show it in this interface. So this is important because many times there's information in this teach panel that you might not care about, like configuration. I don't really care about what configuration I'm using, so I'm going to hide that. There's also a tag user attributes tab. I'm going to hide that one too. And if I do a grab and a release, it'll say what I'm grabbing and what I'm releasing. So I'm going to get rid of those. Okay, so now that I have my teach dialog box reduced, I can slim it down. I can also put it on another screen and operate with these pop-ups on another screen, which is very helpful. The only reason I'm using a single screen is because I'm making a video and I can't do it with multiple screens. So, okay. Okay, so what I've done is I've consolidated my layout a little bit, and we're going to add another robot in here to perform some material handling operations before we have this FANUC robot perform the welding. So what I did was I just basically moved the objects into this configuration, and then I created a state around it. So this is my new configuration, and this just makes it easier for me to have another robot in here to perform the material handling operation. So I'm going to exit 3D simulation, and I'm going back to my bookmarks. And so I had made some bookmarks containing several different robot models, and one of them is a universal UR16. And so in my catalog, I want to use this UR16E, and I'm going to take it and I'm just going to drop it in here. The other thing I did, if you notice, is I shortened one of the pedestals and I just dragged it down. Um, this pedestal you see goes underneath the floor, but you can resize the pedestal inside of SolidWorks, no problem. Once you realize, of course, what the appropriate height should be for it. Because as you know, this is a validation exercise. And so robot risers come in all shapes and sizes. And so you can actually just resize this according to what your findings are from the simulation. Okay, so, and I'm also going to point this robot over in this direction. Now I'm going to double click and make sure that I am at the appropriate angle. Okay. I'm also going to bring in a gripper that I designed in SolidWorks. And this gripper has been processed inside of Robot Programming Essentials. In another lesson that you'll find in the series of videos, we've added kinematics to it, and we also created a port on it. One is a base port to attach to the faceplate of the robot, and the other one is a port that gives us the tool center point. So those are found here. Okay, so going back into 3D simulation, I'm going to mount the gripper onto the UR16 robot. So using the set tool command again, and let me get rid of my widget that's still running from the, here we go. Okay, so I'm just gonna pick the robot and pick the gripper. and it automatically snaps according to the configuration that you have on the port. And so in this port, it looks like it's a good location, and I'm going to say okay. So now I have the gripper mounted onto the robot. And so when I jog this robot, it'll show me that tool point that was on the gripper device. Okay, so let's put this back in a reasonable position. Okay, so I'm going to use this as the home position for the UR16. I'm also going to jog the FANUC robot and put it at a home position that I can use. So I don't want a home position to be over the tool. We want it out of the way. So I'm going to put it somewhere over here so it's clear of the other robot until it receives a go to weld signal. All right, so just bring this in a little bit and we'll just call this our home position. And I'm going to have the system remember this by creating a new state. Here's a helpful hint. Have you ever noticed sometimes when you're picking objects, you're not getting the entire object? That's because you need to reset your pick level. If you right click in space and go to display, you can find the app options tab. And this is where you can reset your pick level so that you can pick the entire object instead of just a piece of it. So I can either update this existing state or I can create a new one. So what I'm going to do is I'm just going to create a new one, and I want my pickup and drop off tables to be blue. So I'm going to create a new state. I'm going to make sure I have all the objects considered. I'll get rid of the old one. Okay, so let's talk about arc welding profiles for a minute. In order to set the right weld speed on this piece of geometry, we have to set up an arc welding profile. And arc welding profiles are different depending upon how thick the weld is or how thick the material is. The thicker the material, the slower the robot moves in order to weld it. So first we set up an applicative profile. And so here are the FANUC profiles, and they're specific for arc welding or sealant deposition or other types of welding. So I'm going to set up an TPE arc start, and the speed's going to be 0.375 meters per second. So whenever it sees an arc start, that's the speed it will apply. And now I'm going to create it for the arc end. And so whenever it sees an arc end command, it's going to apply a speed of 0.05 meters per second. And so that will be the actual speed as it moves along the weld bead. So once the applicative profile is set, I need to now create an arc welding profile and invoke these TPE arc start and TPE arc end number 1. So I'll click on Create Arc Profile, and this is for not just the simulation speed, but also when you're doing offline programming and RRS connections, these speeds will get applied to the robot when it's welding. So when we click on this TPE Arc Start number 1, we can set the speed, and there's a pull down there, but we see that we want to take the speed from that profile that we just set up on this first start. Then while the robot's welding, we want to use the TPE Arc End 1, and we're going to take the speed from that. So when we click on it in this pop-up, we're going to hit it on the pull down, and it applies the speed that we put in the applicative profile. And so this is how we control the robot's speed for welding. And this works in the simulation as well as for the offline programming when you download to the robot and when you're using an RRS connection. Okay, so we're going to start doing some arc welding trajectories. And a trajectory is just a short path, and the way this works is we'll create a bunch of trajectories on the geometry from SolidWorks, and we'll knit them together and create a robot program. So I can create a trajectory on a curve, meaning I can draw a curve in SolidWorks and follow it with the robot. I can use surface intersections. I can use the intersection of parts. And so there's a lot of different ways that we have to choose from. But the one that I like to use and gives me the best results is the surface intersection method. So I'm just going to create a seam between this surface and the next one. When I hit preview, it shows me a representation of where it thinks the seam is. If I click on propagate selection, what that does is it allows me to wrap the path and allows me to go around the corner with the robot trajectory. But I'm just going to create one short one between this surface and this one. So when I hit OK, it shows me where the seam is located at and shows how many tag points it's going to put in it, and also what the direction is. So if I click on the green arrows, I can change the direction, and I can change how many points are located along this seam just by typing it in. It's relatively short. I think 3 tag points is probably enough. There's also different modes that you can use to create the path. You can base it on distance and say that you want to have a tag point every 5 millimeters and it will do it, or every 10 millimeters. It all depends on how you want to specify it. So it's so short. I think 3 is plenty, so I'm just going to use 3. And so now if I click on this tool selection, it takes the torch off the robot and it puts it on the proposed robot trajectory to give me a representation of the orientation of the torch. If I want to see that orientation and if I want to apply an offset to this path, I can take it off the wall surface and off the base surface by any amount, or just to get it off of it. And this makes it handy because you can adjust a robot path very easily using this. So here's a representation of the torch with all of the angles. So this is giving me my base angle, my rake angle, and my roll angle. And so I can easily adjust this just by grabbing one of these green arrows and rolling the mouse. Or if I know what the angle is For instance, I want my rake angle to be something, I can type it in. So it makes it very easy for me to adjust the torch. I want the torch to be located someplace where the robot can easily access it. So I may want to lean it towards the robot. There. Now it's facing the robot, so it's a little bit easier for the robot to reach it. But we shouldn't have a problem reaching this. So now that I have the general orientation of all the tag points, I can look at each one individually. And I can look to see if I'm satisfied with the orientation. So on this last tag point, I notice that there seems to be a little bit of interference when it goes into this corner, and I'd rather adjust the rake angle in this corner so that it's easier to weld and there's less opportunity for it to collide. So I'll adjust the rake angle a little bit. Okay, so now I can just review each individual location. I can check for clashes with the clash button invoked. Now I can look at the approach and the departure. This is handy because it automatically puts in the approach and the depart vectors. You just need to type in what you want the distance to be. So I click on approach, I click on depart, I have a value set. Here's a handy function also, and this is called a skip weld. What this does is it allows us to take a single seam and divide it up into sections. So for instance, if this isn't supposed to be one single weld, but it's supposed to be a series of welds, I can divide it up. So I can divide it up into different sections, and I can just type in how many sections this seam needs to be divided up into, and it automatically does it for me. Okay, so once I'm satisfied with the seam, I click on OK, and there's my robot trajectory for you right there. Here's a helpful hint for you. If you're ever trying to identify where in the tree a part is located, you can always use a right click and then say center tree. And that way the tree will bring you the object. And this also works conversely. You can go inside the tree and locate a specific part and right click on it and say reframe on, and it will bring it into your view. And it makes it easier this way to identify objects and where they're located in the tree or in the world. Okay, so let's get set up and do our second trajectory. And again, I'm going to use surface intersection method. Okay, so there's my base and my wall. Okay, so I want to look at the orientation. And you might notice that this is the same orientation that I used in the last trajectory. So the interface actually remembers the configuration and the angles of the torch. Every time you create a new one, it's going to use the old torch attitude. So I can look at it point by point, check my base angle, add a little bit of rake because I know I had problems in this area, but I'm going to use the clash. I can find out which angle I need to adjust. You can see that a 45-degree angle on the base might not be optimum, but I can play around with my rake angle to see if I can alleviate it. And this might not be the best angle to adjust it. There we go. So once I alleviate the collision, I turn on my ingress and my egress locations, and I say, okay. Now I need to check that I have both of these robot trajectories. And I'm going to merge them together so I can create a robot program. So I'm going to create a task out of them. And I pick on the first one and the second one, and it lists them in the order that the program is going to be. I'm going to name my program. And I'll say, okay. So now I have two individual trajectories and a robot program. The program doesn't show up because remember this, remember the active simulation object? So I have to click on the robot, make it the ASO, and now I can see its program that I just created. So I double click on that program, and now I can see the individual weld points that I just programmed. And of course, I can step through this and look at them individually. And I can dress this program accordingly. So I can look at the individual locations and make adjustments as necessary. Also, remember I put in two home positions earlier. So I can move one to the bottom of the program. And I could use these arrows and move it down through the program, or I can just right click and do a cut and a paste. So cut it from the middle, go to the end of the program, and use paste after. Now I have a home position. It's the same position at the beginning and the end of the program. And I can also use this player to run through what's in the teach panel. And you see how it changed the view because it's using that state that we created. See, it's set as active. So that is where it will return to when you run and when you simulate. Okay, so looking at the program, I can now start doing some analysis on it. The green marks for each location tell me that they're reachable. So I already know that they're reachable. And as you can see, since we ran the program, I now have some beads where I have arc on and arc off. So it runs my weld beads. So I'm going to change a few things. I want to show collisions. So what I've done is I've engineered this robot path to have some collisions. When I change this to a joint move, it's no longer the robot will no longer move in a straight line from the first series of welds to the second series. It's going to use a joint move. And what that's going to do is it's going to drive this torch right through the fixture when I move from the depart of weld 1 to the approach on weld 2. Now here's our collision. And I'm going to activate this. And I know it's active because it turns to color instead of being in black and white. So now I have the collisions turned on. This is a dynamic collision, and so then you can see that as the torch moves through that part, there's a collision there. And it was pretty momentary. So what I'll do is I'll lower this step size setting. So now you can see it with more granularity. So it's easier to spot that way. So now when we simulate this robot and that path, we'll be able to see the collisions that are involved. So I'll click on Run, and then I'll click on the program, and we can watch the robot run from location to location. So I can lower the step size of the simulation, and I can also slow it down. So slowing it down will make it take longer and make it more granular. So another setting I can look at is the step size. And if I lower the step size, I can really slow it down and see the individual locations, and I can see the screen updating. So if there's any question about which robot location has the collision in it, this will help you to make it more granular and figure out what needs to be changed. Okay, so I can identify where in the robot program this collision is occurring by clicking on the name of the location. So if I click on the arc operation, it shows me in the program where it's at. However, remember, this is part of an arc trajectory. I created this initially as a set of tag points inside of an arc trajectory, and that's truly where I want to modify this point. So when I click on the individual tag point, it shows me the arc trajectory that it belongs to. And so then when I double click on that arc trajectory, I can find that individual tag point and go back to the original interface that shows the tool on the individual arc location, and it also gives me that nice interface on where the base angle is, the roll angle, etc. And again, you want to be in the right angle to do this. Let me get a better view here. I want to look at the rake angle. So here's the rake angle, and I can modify it until I don't see a collision and make a modification on that point. So now I modified it in the trajectory. So I can double click on the robot program, and now I can revisit that location in the program. And because I changed the trajectory, we'll see that the robot program is also changed. Because remember, the robot program is referencing the individual trajectories. So at this point, you might be wondering, why did we leave the teach interface to modify the robot program? Because the answer, quite simply, is digital continuity. So we want to modify the arc trajectory. So the robot program references the arc trajectory. What does the arc trajectory reference? Remember the surfaces of the geometry from SolidWorks? So what that means is that when we have a design change on this control arm, if somebody changes the geometry, that means that I would update this arc trajectory according to the new geometry, and these robot locations will assume the position according to that new surface data. So whenever somebody changes the geometry or changes their design, I use a button that says Update Arc Trajectory, and it will update the trajectories according to the new design data.